let's revisit example 3, but this time when we're finding the area underneath the curve, or at least an approximation of the area underneath the curve, we're not going to use the left endpoint or the right endpoint. We're going to evaluate the function at the midpoints of each of these partitions, each one of these subintervals. Okay. So instead of using, say, a fourth and a half and 3/4 and 1, well, I need the midpoint in between these two things. So that's going to be an eighth. Of course, you could take 0 plus 1/4, that's 1/4, divided by 2, and you get 1/8. In between, the midpoint in between 1/4 and 1/2 is 3/8, and in between a half and 3/4 is 5/8. And then finally, in between 3/4 and 1 should give us 7/8. So remember, in this Riemann sum, we are multiplying a function value times the width of that subinterval. And that width we'll call delta x. It is a regular partition, and that regular partition is your b value, which is 1, that's this 1 that's right here, minus your a value, which is 0, that's this 0 that's right here, over however many how many subintervals that you have, which is 4, and there's our 1/4, of course. I went through all those steps, even though it was totally obvious, because we want to be able to do it when it's not, it's not drawn out for us like this particular example is. Okay, so there's our width of our subinterval. We also need our heights, which is our function values. And our function values include, our first one is f of 1/8, and then the next one is f of 3/8, f of 5/8, and then finally f of 7/8. And then we want to add all these things up. This is the thing that's called a Riemann sum. So our area is going to be approximately equal to summation from I equals 1 to n, not to n, we're only doing 4. There we go. If we wanted to do it in general, then we would go up to n. And we need our function value here, that we will multiply times our width, and we know our width is supposed to be just 1/4 for this particular example. So let's see if we can come up with our ith x value, the x sub I, x sub I, and that's each one of these numbers that are right in here. We have to try to generalize it. We'll generalize it with understanding that this one is I is equal to 1, I is 2, I is 3, and I is 4 for this last one. Well, we can see that we have 8 on the bottom of each one of those, so at least let me put that in here, divided by 8. Now take a look at all of the numerators here. It's 1, 3, 5, 7. What would be the next one? 9. And the next one, 11. Those are all odd numbers. And odd numbers are defined as either 2i plus 1 or 2i minus 1. Let's decide which one we're going to use. Well, if we stick in 1 for this first one here, 2 times 1 gives me 2, plus 1 more gives me 3. That's not what I want. How about if I stick in 1 to this second one down here? 2 times 1 is 2, minus 1 does give me 1. If I stick in 2, 2 times 2 is 4, minus 1 gives me my 3. If I stick in 3, 2 times 3, erase. 2 times 3 is 6, minus 1 gives me my 5. Yes, I think we stumbled upon the answer, 2i minus 1. If you needed to generalize it, and we will shortly. But for right now, if I'm going to add up all of these things, it's essentially just f of 1/8 times 1/4 plus f of 3/8 times 1/4. 5/8, f of 5/8 times 1/4. And then finally f of 7/8 times 1/4. You get that, f of 1/8, of course, by just plugging that thing into the function, right? It's 1/8 squared, and then you're going to multiply that times 1/4. Add up all of those things, and you should get 0.3 34375. Okay, so here is the midpoint sum. We also had a left Riemann sum and a right Riemann sum. And notice that this number, if you recall, let me see, I can go back in time here. That number is someplace in between these two things, right? And it's a better approximation than either the left or the right. And that's, in general, a true statement. The midpoint sum gets pretty close to the actual area underneath the curve much faster than either the left Riemann sum or the right Riemann sum. You can almost visualize this as, hey, you see this little extra piece? It could fit almost nicely right in here, and this little extra piece can fit almost perfectly right in there, and so on. All right, we still have one more sum, one more approximation that we often do. We have the left Riemann sum, the right Riemann sum, the midpoint, and then the last one is going to be a trapezoid.